Hello and welcome. In this lecture, we're going to look at some, I guess, yet another way to draw molecules. So we've looked at Kekulé depictions of molecules, and they're very helpful, but there is actually yet another and probably the most popular way of depicting molecules, and that is called bond line structures. So without further ado, okay, so bond line structures. So let me set up the issue a little bit here by first saying, imagine that we have ethanol, everybody's favorite alcohol. So ethanol is C2H6O. So the way that we would start is we would connect our carbons and then add our oxygen to the end. So carbon is a group 4 element, and it requires then 4 bonds to reach its octet. So we're going to put 3 of the hydrogens around the first carbon, 2 around the second carbon, and then 1 around the group 6 element oxygen. And it's a group 6 element, so for it to have an octet, it will only need to bond to 2 different elements because it has 2 pairs of unpaired electron, or excuse me, 2 pairs of electrons, 2 lone pairs of electrons. Okay, sorry about that. So another popular molecule for everybody is octane. It's what we put in our cars, and it is C8, hence the name octane. And then to fill up everything, it's going to have 18 hydrogens. So we start with 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So it turns out that we just write the hydrogen atoms around the carbon atoms however we want to do it, and if every carbon has 4 things attached to it, 1 or 2 of which could be carbon and the other 3 or 2 of which could be hydrogen, we get to 18 hydrogens. All of the carbon atoms have an octet, all of the hydrogens have an octet. So we have 2 molecules. Okay, my point in drawing these 2 molecules was, I guess, further practice with Kekulé structures, but also to kind of emphasize how much it's kind of lame to draw Kekulé structures. Yes, all elements have an octet, but there is another problem, and it's a practical problem, but we're pragmatists in this class. It takes too long. I don't know what too long is, but it takes a long time anyway, too long to draw organic molecules as Kekulé structures. Okay, so let's introduce a new form of bonding, and it's really the best and the fastest way. So going on to another page, there is the bond line depiction or bond line structures. Okay, so bond line structures, the bond line depictions, they have a lot of advantages. If you draw molecules as bond line structures, you can get them done faster. So drawing them, the bond line depiction is fast. Additionally, I believe it is not boring. It was just so boring to write C's and H's when we were looking at ethanol and octane. So it is not boring. My students have told me it's not boring. It's just less boring. Whatever. Okay. To each their own. So how does this work? What do bond line structures do for us? Okay. So I'm going to draw the Kekulé structure of butane, which is a straight chain molecule with 4 carbons and then however many hydrogens it needs. Turns out it needs 10. Okay, so this is Kekulé. It should look familiar at this point. What I'm going to do is I'm going to redraw it as a bond line structure. Okay, a bond line structure. This is butane. What is butane, you might be asking? So I'm going to highlight it here. This lightning bolt looking thing is butane. Okay, so what is going on here? Number one, we do not draw H's, but their existence is implied. But their existence is implied. Number two, we do not write the letter C, but we do draw C-C bonds. And really, I should be more clear here. We draw them as a zigzag. Okay, so let's break down this structure of butane and kind of talk about how we've accomplished all of these things. We've avoided writing the letter H altogether, and any carbon-hydrogen bonds have also not been drawn. We've also avoided writing the letter C. I really like not writing the letter C because when we drew octane, I was getting kind of bored of writing the letter C over and over again. So let's look at this butane molecule again. Now, maybe you don't need it, but just in case, I'm going to redraw the Kekulé structure, kind of small over here, so we can see what we are after. Now I'm going to take advantage of my ability to write with multiple colors, and I'm just going to point out that what we have with this molecule are 4 sort of points at the molecule where we change direction. So each of these dots is a carbon atom. And maybe it's helpful if I see. So there's 4 of them, 4 carbon atoms, and there's 4 dots in my structure. Where do the dots come from? They come from an edge or vertex or vertice, whatever, an edge or a corner, edge or vertex / corner in our structure. So every time we sort of change direction for the most part, or change something about the molecule, that represents a carbon atom. Additionally now, in addition to having little points that represent the the atoms, we have lines that represent the CC bonds. So we have CC bonds, and if you look, even though there are 4 carbon atoms, they can only be connected by 3 carbon-carbon bonds. So we draw the carbon-carbon bonds as lines, but we introduce changes of direction, vertices, corners, that sort of thing, so that we get, so that we're able to better visualize the number of carbon atoms. Okay, so imagine that if you drew it without the zigzags. And this is, again, bad. It would look like this: 1, 2, 3, 4. Is this really a carbon? I mean, I could put red dots. Oh, I added an extra line, didn't I? It's not 4 lines, it's 3 lines. Okay, I mean, I could add my dots, but we're trying to do this fast. We're trying to be efficient here. And not everybody has red pens available when they're trying to draw molecules in the back of envelopes, which is a really fun thing to do, by the way. Okay, so we drew the number of bonds, which were 3 in this case, only to carbon. We avoided all of the bonds to hydrogen. We avoided writing the hydrogens all together. And we really didn't write the letter C at all, but we showed the existence of C by having little corners or edges of our lines and our bonds. So that's where the molecule comes from. So, you know, one thing that we should just right away do is we could go with, let's count the number of C atoms in each structure below. So we count the number of C atoms in each structure below. So this molecule, this molecule, this molecule, this molecule, this molecule. This molecule. Okay, so we've got a few examples in front of us. What I'm going to do is I'm going to stall so that you can pause the video and then potentially work through these on your own, and then I'll go through the answer by writing red dots. I'm continuing to stall, I'm continuing to stall, I'm continuing to stall. I'm now done stalling. Okay, so get my red pen. I'm gonna make a dot. So the edges of our molecules always end up being carbon atoms, and then every part where we change direction. So this looks a lot like butane, but it's longer. If we count 1, 2, 3, 4, 5, 6, 7, 8. So I've got, in this first example, 8 carbons. Now what I'm going to do is I'm going to get my red pen and I'm going to make dots at each of the carbon atoms, and you can kind of compare your notes and see if you had a similar analysis. Some of these are exceedingly hard. This other one's got what we call branch points. It's just some carbons pointing in separate directions, but they still are edges or vertices or changes of directions, and they still count as carbon atoms. Got a little sloppy with my hexagon. The molecules can exist in rings, and these rings take on very regular shapes. Just redrawing that. I still had an overlap down here, whatever. Okay, so they can be hexagons. If we've only got 5 carbons, then we're going to make a pentagon. Now there's 2 lines connecting these 2 dots together. Those 2 lines represent just double bonds, okay? And we've talked about double bonds before. Now, there's something really weird. If you've got a triple bonded structure, it turns out it wants to have what's called a linear geometry. More information on that in the upcoming lectures. But because of that, we always draw triple bonds as linear arrangements. And that's something that's a little bit harder to get a hold of. But as you start at the edge of your triple bond, you've got a carbon. At the edge of your molecule on the opposite side, you've got a carbon. So those 2 carbons. And then as you change from a triple bond to a single bond, that is also a carbon. So looking at our counts now, we've got 8. We've got 1, 2, 3, 4, 5, 6 carbons. We've got 6 carbons. We've got 6 carbons, 5 carbons, 4 carbons. 1, 2, they're double bonded, but that doesn't change the carbon count. And then the last example is 3 carbons. Okay, so those are some examples. There's some more worksheets on this. We'll all get a lot more comfortable with this in time. Now, what I want to do is move on to another aspect of bond line structures, and that is the implicit hydrogen. The implicit hydrogen, these are the H atoms that exist but are not drawn. That is to say, their existence, what's that mean? Might be an E, whatever. Existence is implied. So their existence is implied, hence they're called implicit hydrogen atoms, okay? The implicit hydrogen. So we don't write these out, but their existence is implied. So if I draw something like this, this molecule is C3H8. Okay, how do I know it's C3H8? Well, turns out that if you drew the Kekulé structure of this, I'm just going to go ahead and draw the Kekulé structure. There are my 3 carbon atoms. They represent the edges and the vertex. These are my 3 carbon atoms. For them to have an octet, we must put these hydrogens on. So if I surround the molecule with hydrogen atoms, then every carbon atom has an octet. So carbons have as many H atoms as they need. If they don't have that number of H atoms, like if this central carbon didn't have 2 hydrogen atoms, it wouldn't have an octet, and that's not good. So what we're doing here is we're just not writing the H atoms, but we're assuming that their existence is implied, and because the carbons must have as many H atoms as needed to have an octet. So that central carbon atom has 2 hydrogen atoms because it needs 2 hydrogen atoms to have an octet. If we introduce double bonds, yes, that changes things a little bit. So what you need to do is be able to look at a structure and not only count the number of carbons, 3 in this case, 2 of the carbons are double bonded to each other, and also count the number of hydrogen atoms. Okay, in this case, we only have 6 because we introduced 1 double bond, so we need 2 fewer hydrogen atoms. Let's look at that from a Kekulé standpoint. So the end carbon needs 3 to get an octet. The middle carbon now only needs 1, and the leftmost carbon needs 2. That is 6 hydrogen atoms total. Okay, so hydrogens, the letter H is not often drawn because its existence is implied if it's bonded to carbon. Now, what about other elements? When bonded to other elements, that is to say, other than carbon, H must be drawn explicitly. Okay, so let's take a look at ethanol again. And this time, what we're going to do is do the exercise from the opposite side. So instead of going from the bond line structure to the Kekulé structure, we'll go from the Kekulé structure to the bond line structure. And what this molecule is going to look like is one of a few possibilities, okay? So it's going to be this, or it's going to be this. And it really doesn't matter where you put the oxygen, just as long as it looks like it's, the hydrogen, as long as it looks like it's bonded to the oxygen. So these 3 possibilities. So what we have here are we've got carbon, 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 carbon. Now each of those have as many hydrogen atoms as they need. Their existence is implied. We're not going to write the letter C explicitly in this case. We're going to let its existence be implied. Those are implicit hydrogens. So 5 of the hydrogens on ethanol are implied. 1 must be explicitly drawn, and that's the one that's not bonded to carbon. So they must be drawn explicitly. So this explicit hydrogen that we've got drawn is bonded to an oxygen atom, and it must be drawn. So this one must be drawn. Now we've got some flexibility. Do we want the hydrogen to point upwards and to the right? Do we want the hydrogen just sitting right next to the oxygen? Do we want the hydrogen pointing down? Any direction it wants to point is fine, or just crunched up without even writing the bond is also fine. I realize that doesn't seem super correct, but it's just how it works. The thing that is not correct, the thing that we must avoid is this is fine, this is fine, even something like this is fine. It's just rolled around in the universe a little bit. But something like this is bad. Okay, it's bad because we're missing the explicit hydrogen. We must write that out. Okay, so that's kind of the gist of bond line structures. We look for ways to avoid writing the letters C and H as much as possible. That makes writing the bond line structure so quick. You saw previously in the notes, just going a few pages back, we were able to, I was able to write, 7 structures fairly quickly and be a little bit creative about it because I relied on this shorthand notation for writing molecules. If I had to write C's and H's for all of them, it would just get way too cumbersome. But we don't want to lose all of the H's. It's really helpful to see H's that are bond to non-carbon-based elements. So for example, let's do this. Let's draw for C2H7N, draw a Lewis dot, Kekulé, and bond line. As you're learning these, it's helpful to progress in this order, starting with the Lewis dot structure, the most laborious, but generally the most helpful because you actually see all the puzzle pieces by themselves with their correct valence electrons. And you can practice sort of connecting them in such a way. Once you have those connected, it's pretty simple. If you've got a good Kekulé, Lewis dot, it's pretty easy to draw a Kekulé structure at that point. But as you practice this, you'll find that you can look at molecular formulas, immediately go to the Kekulé structure. Be advised, though, for the first exam, you must be able to do all 3, and then we'll move exclusively into one that I hope we all master, which is the bond line structure. So we're going to start with the Lewis dot structure. We're going to connect our carbons together. Multiple ways you can do this, several different answers. I like to connect my carbons together first, taking advantage of our favorite aspect of carbon chemistry, which is bonding to other carbon atoms. Then I'm going to connect the other non-hydrogen element, which is nitrogen, and then count how many dots I have around the side. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Oh, I miscounted the first time. Okay, that makes sense. So we have 7 open sites. We're just going to write H's around the outside then. We're going to double check our formula. Do we have 2 carbons? Yes. Do we have 1 nitrogen? Yes. Do we have 7 hydrogens? Yes. You wouldn't believe how many people take the exams from me and just don't have the number of elements that are in their answer match the number of elements I tell them they have to have. Okay? Pretty easy way to lose points. Okay, so Lewis dot structure complete. So we have Lewis dot done. As I said before, Lewis dot to Kekulé isn't too hard. You just convert the horizontal, the sort of bonding double dots into straight lines. So that looks like this. It's important, though, when you draw Kekulé structures to, as best that you can, remember to draw lone pairs of electrons. So this is Kekulé. Okay, so how do we convert a Kekulé structure into a bond line structure? Well, as soon as you put your pen to paper, which I've done with this dot right here, I started drawing a line. But as soon as I put my pen to paper, that first dot I made is a carbon atom. So I've already drawn carbon 1. Now I'm at carbon 2. And now I'm at carbon 3. There is no carbon 3. It's now nitrogen. So instead of drawing an edge or vertex or dot, I'm going to make sure I write the letter N. Okay, so what do we have to draw in terms of H's? We've got all the other elements drawn. What about the H's? Well, you only draw H if it's not bonded to carbon atoms. So that's just our hydrogens. I like to take advantage of sort of a zigzag architecture that we'll all get more comfortable with as we draw more of these. And we'll see why it's really helpful to have the zigzags in there. But I have one going up and to the right, one going down into the south. Turns out that if we actually look at bonding architectures and geometries, this fits most closely with that structure. So with, as you saw before, as I sort of hinted at but didn't write explicitly, with bond line structures, it's helpful, but it's not required to draw lone pairs of electrons. And as I said before, I'm going to scrunch this down here. If you run out of space, as I have, sometimes you can get away with even just writing the H's scrunched into their non-carbon atom. And here, in this case, we have 2 of them, so we write NH2. That is also fine. I feel like something like this, without that scratchy looking hydrogen, I feel like something like that's a really good one to start with because it just shows that you haven't forgotten about the lone pair of electrons on the nitrogen atom, and it shows that you're understanding which direction the hydrogen atoms will be bonding off of the molecule. And we'll get better at looking at the zigzag architecture as we go forward. Let's look at just a few more examples. So what I'm going to do is I'm going to convert, this is really good practice, convert Kekulé to bond line. I'm going to do 2 examples before we break for this lecture. Okay, we've got this example. We've got okay, so got a couple of examples here. What we want to do is convert these to bond line structures. These are both Kekulé structures as they have been drawn. So the first thing that we recognize is we have a chain of 4 carbon atoms across in this first one. So I'm going to put my pen to paper, make a dot. That's my first carbon. That's carbon 1, zigzag to 2, zigzag to 3, zigzag to 4. There's my carbon chain framework. I've got a couple of double bonds in here, so I'm just going to add those. Got one going from the first 2 carbons. I don't have a second bond going from the middle 2 carbons shown there and there. That is to say, these 2 carbons are not connected by a second bond. So I'm going to leave them alone, but I will draw a second bond to the 3rd and 4th carbons. So there's my bond line structure. If I was working, you know, it'd look a little bit nicer, hopefully, if I actually had a pen and paper. It's a little bit hard with the lack of resistance on this glass screen. Okay. Now I'm going to do the same thing here. I sort of digest the fact that I immediately have a 3 carbon chain. So I'm just going to create a 3 carbon chain. Put my pen to paper, that's carbon 1, up to carbon 2, down to carbon 3. Now, carbons 1 and 3, which I've shown as dots, are CH3 groups. That is just a carbon with 3 hydrogens. And so we don't actually need to do anything else to this group because it just has hydrogens bonded to it from now on. We've already drawn the carbon-carbon bond to this vertex. Now this vertex in the center is kind of interesting because it has an oxygen atom attached to it. Now it may be necessary to sort of delete your dots at the end of the day because on the edges so that you don't mix them up for lone pairs of electrons. That's really helpful. But I just draw 2 lines going up to an O. The O doesn't have any H's in this case, so I just write it as an O. I think it's helpful in the early going at least to draw lone pairs of electrons. Okay, I want to sort of keep going and just look at some more examples. One thing that I mentioned earlier is the triple bond. So with triple bonds, the conversion of this to bond line looks like this. That is, there is a carbon in between the break of a triple to a single architecture. But we draw it as a straight line, as a linear arrangement, because that is what's sort of most correct when you're looking at a structural perspective. So if I had something like this, really complicated molecule, I would convert it, I could convert it from the bond line structure. Sorry, let me regroup and tell you I'm converting from a bond line structure to a Kekulé structure. I hope I have room for all of this. But starting at our first carbon, we go to a carbon to a carbon. Then I'm going to go to another carbon. Now this next carbon, got the first 2 carbon atoms drawn, but then the 3rd carbon is part of a triple bond. And so I can't forget that my change from a triple bond to a single bond comes with an additional carbon atom. Okay, so I'm now at the second red dot. So I have to go down to a corner, which is another carbon atom. And then I go up to a carbon that's double bonded to oxygen and has a single bond to an O. And I should be consistent, that O has an H. Okay, so now I just add H's as necessary so that my carbon atoms all have a filled octet. Notice I don't add any hydrogen atoms to triple bonded carbons that are buried within a chain. If they were at the edge of a chain, I would need one hydrogen atom to be added. Okay, let's do just one more example just because I think it's helpful. And that will be ring structures. So rings aren't overly complicated. If you've got something they're not overly complicated relative to anything else we've been doing. They follow the exact same rules. So this is a really important molecule. It's called benzene. It's a ring of carbons, and they alternate double bond and single bond attachment points. If I converted that from a kekulé to a bond line, it would look like this. So a hexagon with alternating double bonds and single bonds. Okay, so a lot here. This is a harder lecture to just know everything and be awesome at everything immediately. Still, with that being said, bond line structures, drawing them, interpreting them, depicting them, converting them is one of the most important skills you'll gain in this class. I think it's really important to just pull off the Band-Aid, show you everything that's out there. There's just kind of a few simple rules. Don't minimize the times you write the letter H. Don't write the letter C if you can, and then write all the other letters. It makes for drawing the molecules fairly easy. But even with just a few rules, getting to that point of mastery takes a little bit of work, but we can get there. Okay, so hopefully there's a lot of practice with the discussion problem sets. There's things to kind of watch out for. There's a ton of resources on this online, drawing bond line structures. So just kind of, if you need extra practice, search. Really, every molecule that can be drawn can exist as both a bond line structure and a kekulé structure. So going back and forth between the two would be great. Additionally, and then I'll be quiet, you could just look up important molecules, like what's aspirin, what's morphine, what's Viagra, all these molecules that are active ingredients in drugs. If you look them up, you'll see a bond line structure, see if you can count the number of carbons and hydrogens and that sort of thing. Okay, with that, I will end this lecture, and we'll move into the final lectures of Module 1 soon.